Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper trending on X, published on January 29, 2026, about 5 days ago. It introduces a unified single-model approach to video dubbing that handles audio and visual generation jointly, hitting a 100% success rate in challenging settings where modular baselines often fail. The paper is titled Just Dub It, Video Dubbing via Joint Audio-Visual Diffusion. And, as we'll see later, the results for synchronizing environmental sounds and maintaining speaker identity are quite significant. Figure 1 illustrates the core concept using a concrete example. At the top, the input video features a girl speaking English, interleaved with a dog barking, which creates a complex audio mix. The middle section shows how the proposed unified audio-visual model processes this without separating pipelines for voice and lips. Finally, the bottom panel displays the result where the girl now speaks Spanish with synchronized lip movements, while the background dog bark is preserved perfectly in the new audio track. Well, Figure 3 illustrates a fundamental problem the authors call the identity pronunciation trade-off. On the left, simply generating the dubbed audio from scratch gets the Spanish pronunciation correct, but completely fails to capture the speaker's original voice. In the middle column, if the model conditions on the original English audio to preserve identity, the English accent and prosody leak through, causing the Spanish output to sound mispronounced. The solution, shown on the right, resolves this by conditioning on a reference clip that captures the target language's phonetic style while maintaining the speaker's identity. To address the scarcity of aligned training data, Figure 2 outlines a clever synthetic generation pipeline. It starts at the top by creating a video that naturally switches languages, such as a speaker going from English to French. Then, looking at the bottom left, the system masks the mouth and audio of the French segment. An in-painting model fills this gap to transform the speech back into English. This yields two perfectly aligned clips, one in French and one in English, that share identical head motions, providing the necessary ground truth for training. With the data pipeline established, Figure 4 details the actual training architecture. At the bottom, the system takes three inputs: the clean context video and audio, the noised target versions, and a text prompt guiding the translation. These flow into the central audio-visual transformer blocks. Here, the main model weights remain frozen to preserve pre-trained knowledge, while only the low-rank adaptation layers marked with the fire icon are updated. To keep everything synchronized, the grid at the top right represents a special cross-attention mask that prevents the noisy signals from peaking at the wrong modalities. So, Table 2 evaluates the audio quality, comparing this unified approach against specialized audio-only baselines like Cozy Voice and Open Voice. The most dramatic improvement appears in the duration error column, where the unified model achieves nearly perfect temporal alignment, dropping to roughly 0.05 seconds on the challenging benchmark. In contrast, the baselines struggle with errors closer to 2 seconds. Additionally, the intensity correlation scores are significantly higher for the proposed method, which confirms that it captures volume dynamics and environmental sounds much better than the alternatives. Alright, while the previous table covered audio, Table 1 assesses the visual quality and synchronization. Looking at the challenging benchmark section at the bottom, the difference is stark. Modular baselines like latent sync struggle here, with success rates dropping to 80 or 74% because their face detectors fail on complex inputs. In contrast, the unified model maintains a perfect 100% success rate. Furthermore, the F versus D scores, which measure temporal coherence, show that the unified approach produces much smoother video, cutting the error score nearly in half compared to the competitors. So, while the previous table gave us the stats, Figure 8 shows what those failures actually look like in practice. The top block tests profile views and occlusions, while the bottom block pushes the models with non-human animated characters. Notice the red error boxes in the latent sync row. That model completely crashes when standard face detection fails on complex inputs like the Joker or Zootopia. Meanwhile, the Hey General row often displays visible square borders around the mouth, marked here as copy-paste artifacts. In contrast, the proposed method in the bottom row handles these extremes seamlessly because it generates the audio and visuals jointly, rather than pasting a cropped mouth onto a static background. Wrapping up, two key takeaways stand out. First, shifting from modular pipelines to a unified audio-visual model eliminates critical failure points like face detection errors. Second, generating synthetic training data via in-painting effectively solves the lack of paired multilingual videos. This suggests the future of dubbing lies in holistic, generative models. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.